complete our discussion of the superconformal index. And then B, there's not much left to discuss, so we can hopefully do that fast. And then we will move on to a discussion of four-dimensional gauge theories. Okay? So,
Can you explain how these matrices represent the half-integral construct?
which, the superconformal index? I could if you want. Yeah, I hadn't planned to, but okay, I can do it, yes. Sure. Okay. Okay, then I think we will not move beyond the superconformal index. Okay. So, excellent. So, so in the last class, you remember we looked at these chains, right? We looked at these chains where J was decreasing and the R's were increasing, right? We had an R1, I think. R1 was increasing, J was decreasing, and all those characters contributed to the same. It was the number of one minus the number of the next, plus the number of the next, minus the number of the next. That guy was conserved. Right? You remember that discussion that came from what can happen, what quantities, individual numbers of short representations were not conserved because it was possible for two short representations to combine together to make a long representation. But by studying the ways in which short representations could combine, because if an has to combine with either an plus 1 or it has to combine with an minus 1 in order to go up, then number of n plus 1 minus number of n plus number of n minus 1 minus number of n plus 2, n minus 2 and so on, that thing was absolutely conserved because any combination would leave that thing unchanged. Right? And that's, so that was our technique for inventing things that would necessarily be non-renormalized, numbers of linear combinations of numbers of short representations that would necessarily be non-renormalized as a function of coupling. Okay. Now, in this lecture, I wanted to briefly tell you about another more physicsy way of thinking of this. This was a sort of mathematical way of thinking, right? You have representations, they combine, blah, blah, blah. Okay, I wanted to tell you about another more sort of physicsy way of thinking of it, which goes as follows. Look, we have the superconformal algebra, and you remember that our Q's, okay, our Q's, they transformed in the fundamental of Un, and they transformed as spinors of either SU2 left or SU2 right. In fact, the thing we called Q bar transformed as a spinor of SU2 right. The thing we call Q transformed as a spinor of SU2 left. And we've got SU2 left and SU2 right. You remember because the conformal group in this dimension was SO4 comma 2. And the SO4 part of that was SU2 times SU2. Right? This is the usual. Okay. So I'm going to study a particular Q, not a Q bar. And I'm going to study the one that had highest weight in UM and lowest weight in J. Okay, so I'm going to study the guy that I'm going to call Q minus half comma 1. What does this mean? This means that the charges of this guy were J1 equals minus half. Of course, J2 is equal to 0 because it's the spinor of SU2 left, nothing to do with SU2 right. Okay, and whose SUM quantum numbers are 1, 0, 0, 0 in the notation that we talked about last time. Okay, so this is the guy with the highest charge. So what was the notation we talked about last time? I think the first guy, a guy labeled the number of, right. The first, you see, last time we talked about a notation for representations. Okay, I think that our charges were the number of columns of length m. Okay, so the first guy was the number of columns of length 1, the next guy was the number of columns of length 2, and so on. Okay, and now there is a particular Cartan charge whose eigenvalue in the highest weight state gives you this number of columns. Okay, so when I'm writing the when I'm writing this charge here as 1 0 0 0, it's the weights under those Cartan charges. Okay, so let me say again, this representation, all I'm saying is that this is the highest weight state. Because you see, this was in the representation 1 0 0 0, because it had one column of length 1, no columns of length 2, no columns of length 3, and so on. And what I'm saying, all that I'm saying here is that we're looking at the highest weight state in that charge. Okay, for instance, suppose we were taking SU4, which is the same as SO6. Okay, then this would be the charge with all Cartans being so then this would be the SU4 vector would be the SO6 spinner, and this would be the charge with all Cartans H1, H2, H3 being plus half. So just as high as you can go in some convention. Of course, high, low depends on what your basis is. We're choosing a certain basis and we're taking the size. Okay. So this is the charge that I'm looking at. Okay? This charge I'm going to call Q. And its complex conjugate, its Hermitian conjugate, is some particular S operator. I'm going to call that S. What are the charges of S? Well, S has opposite charges from Q because it's a complex conjugate. So it has charge J equals plus half, J1 equals plus half, J2 equals 0, and these SUN, oh, and I forgot to say this also had R equals 1. The U1 charge, R is equal to 1. Okay? And this guy will have charges minus 1 0 0 0 0 under these particular Cartans. I'm not describing this in more detail because I don't want to take 15 minutes to define my basis of SUM and so on. It's not going to matter very much. Okay? One can do it in full detail. Okay. R would be minus 1 for the S operator. This was yeah, forget this. Just forget this notation. Just let's look at these charges. Okay, there's a particular supersymmetry with these charges. There are many supercharges. One of them has these charges. And I'm going to look at this particular guy. Okay? Now, if I look at this particular guy and I write out the superconformal algebra, the part of the superconformal algebra that tells me about the commutator of Q with S, anti-commutator of Q with S, it turns out to be the following. Okay, so RKs are these various SUM Cartan charges, under which, under R1 we had, Q had charge 1. Okay, and this R is the U1 SUM charge, this J1 is J1Z of SU2 left. Okay, and J1 Z of SU2, J2 never appears, basically because this Q knows nothing about J2. Okay? So these anti-commutation relations just, we wrote down in the last class the structure of these commutation relations. I'm just choosing one particular charge. Okay? And you recognize this thing, right? We had similar expressions from last time. Okay, excellent. Now, why have I written this down? Why have I written this down? I've written this down for the following reason. Suppose, what is the most general partition function I can compute in a superconformal theory, where I weight with chemical potentials with respect to the various charges that appear in the superconformal algebra? So the most general partition function I could compute is something like this: e to the power minus beta h, okay, plus let's call it zeta 1 j1 plus zeta 2 j2. Let's just so that I'll put all minuses just for fun. Zeta 1 j1 plus zeta 2 j2 plus zeta m rm. Let's call these mu m rm plus let's say I don't know r phi times r. The trace of this object is the most general character I could consider in the superconformal algebra, because this weights with respect to the maximal set of commuting charges, which are these Carsan charges. Okay? So you can think of beta as like an inverse temperature and all of the others like generalized chemical potentials. Chemical potentials for these various other charges. Okay? Some of them will have names. For instance, beta, if I write zeta 1 as minus beta omega 1, that would be the traditional way of putting a chemical potential for angular momentum. And omega 1 would then be interpreted as an effective angular velocity, if you were. Okay, but right, for current purposes, I don't care what they are. This is just formal analysis. Okay. Now I take this object and I choose the following. I choose my betas to obey this, betas and zetas, mu's and phi to obey the following condition. Beta minus 2 zeta 1 minus 2 m minus k by m mu m mu k. Okay. This m is, we have, m is SUM. How many supersymmetries we had? Thank you. Mu k minus 4 minus m by 2m into phi. Suppose I choose this to be 0. So I don't compute my partition function at arbitrary values of the chemical potential, but I demand the following relationships between chemical potentials. Is this clear?
Why is Hamiltonian 1?
Hamiltonian is not 1. This is just a relationship between chemical potentials. Now, why have I chosen this relationship? Maybe that's the question. I've chosen this relationship because so suppose I choose any set of B's such that betas, zetas, mu's and phi's, but such that this relationship is obeyed, then the weight of Q under these chemical potentials will be 0. Okay? Because what I've done here is chosen H to be the, that's maybe your question. This was half. Here, H was the charge of Q, the Hamiltonian dilatation charge of Q, which was half. Okay? J was the, I've messed up in bad way. I'm so sorry. I'm sorry, I wrote this relation completely wrong. Let me write it again. Instead of putting these numbers here, which is what I did, I should have put the charges of Q. Sorry. So I'm going to choose minus beta by 2 minus zeta 1 by 2. Okay? No zeta 2 plus mu 1 plus phi is equal to 0. Sorry, everything's minus. And plus theta, yes, minus, because this was minus. Thank you. Plus, but this is minus. Thank you. So this was plus half, this was minus half, this was 1, and this was 1. Yes. Sorry about that. So I'm going to choose the chemical potentials such that these chemical potentials, when such that chemical potential times charge, which is weighting factor, when evaluated on the charges of Q, equals 0. Now remember that S has minus the charges of Q. So it's also true that chemical potential times charge, when evaluated on the charges of S, equals 0. Okay? So now, if we look at such a trace, and we also add a minus 1 to the power f here. Okay? So we're going to look at this trace here, subject to this condition, with this minus 1 to the power f. Now if you take a state psi that contributes to this trace, okay, and you take the state q psi that contributes to this trace, then these two contributions are equal as far as all these charges are concerned, because Q carries 0 weighting by e to the power mu I hi by construction. However, Q has fermion number minus 1. So these two states will cancel in their contribution to the index. Now, the same is true of psi and S psi. Okay? If you have a state psi and that state is gives you a certain contribution to the index, okay, then the state S psi will give you an equal and opposite contribution to the index. Okay? Now, see, the commutations relations of Q and S depend on whether the right hand side of this thing here is 0 or not. If the right hand side is 0, we've got anti-commutator on that set of states, Q, anti-commutator of Q with S is equal to 0. But remember, Q was S dagger. The only way that Q S plus SQ can be 0 when acting on a state is if both Q and S annihilate that state, because you take the expectation value, right? So suppose we have two cases. Case 1, charges are such that RHS equals 0. In this case, we have the commutation relation is QS equals 0, okay, and states with those charges, we sandwich this relationship between, so QS plus SQ psi is equal to 0. Now each of these two expectations is positive definite, so each of them must be 0, okay, and any one of them is 0 if psi is annihilated by, this guy is 0 if psi is annihilated by S, and this guy is 0 if psi is annihilated by Q. Is this clear? I'll just write this out. So that's psi qs psi plus psi sq psi is equal to 0. Always remember that S is q dag. Okay? So this is the same as norm of S psi plus norm of q psi is equal to 0. So 0 is the sum of two positive numbers or non-negative numbers. The only way that can work is both numbers have to be 0. Okay? So we get that q psi is equal to 0 and S psi is equal to 0. Because we're looking at this when acting on states such that the charges add up to 0 on the right hand side. Suppose, okay, let me say this more clearly. Whatever appears on the right hand side, that combination of charges, this h minus 2j1 plus whatever, let's call that whole thing delta. So suppose we look at states that carry delta equals 0. Okay? So this was case 1. Charges are such that RHS is 0, that delta is equal to 0. Okay? If that's the case, then we've just shown that both Q and S annihilate those states. Okay? So there's an equivalent, of course, if Q and S annihilate the state, then the left hand side automatically is 0. So there's two equivalent ways of saying something. First way of saying something is states carry delta equals 0. Second way of saying that thing is that all states that states are annihilated by both Q and S. These are equivalent statements. Being annihilated by both Q and S is the same as being annihilated by delta. Okay? On the other hand, we have case 2. Case 2 is delta not equal to 0. If delta is not equal to 0, it's got some value, we can always renormalize S and Q by the square root of that value. And then we get the commutation relations of the fermionic harmonic oscillator. We know that the fermionic harmonic oscillator, its quantization produces two-state systems. Okay? And the two-state systems are states which are, one of the states is annihilated by Q, the other state is annihilated by S, because A and A dagger. Okay? So if I call one of these two states, let's say psi, the other one will be either Q psi or S psi. So all states appear in pairs because it's just the implementation of the harmonic oscillator. And these pairs are such that their contributions to the index vanishes. And therefore we conclude that this index only receives contributions from states that are annihilated by both Q and S, or equivalently only receives contributions from states with delta equals 0. Is this clear? Okay? Yes. When we evaluate this at values of chemical potentials that obey that equation. No statement being made for more general chemical potentials. Okay? Wonderful. So, we have concluded that if we evaluate this particular trace, okay? If we evaluate this particular trace,
you should have used the weights for the psi. You are calculating this right hand side with respect to psi, right?
yes.
And then what the numbers you are using is coming from Q.
In that condition, yes.
Yes. So you don't need to impose the condition for S.
S has charges which are minus those of Q.
All the charges are minus.
All the charges are minus. Delta is minus half. That's why it's complex conjugate. Okay? So the condition that we use for Q also is the same as the condition for S. Okay, good question. So we see that this index only receives contributions from states that are annihilated by both Q and S, or equivalently contribution from states with delta equals 0. Okay. Now, you can ask the following. You can ask, are there any states in any long, is there any long representation that carries states that are annihilated by both Q and S? And the answer is no. Just because in long representations Q and S act like this harmonic oscillator kind of thing. You know, long representations are the representations in which no raising operator annihilates a state. Okay? So, for instance, you act with a Q, with every possible Q, you will get some state. And then when you act, you take, let's say, a primary, you act with Q on it, you get something. Then on that, when you act with S, you get something non-zero. Okay? So one can seriously check that there is no long representation that carries any states that are annihilated by both Q and S. Of course, the long representations, all long representations carry states that are annihilated by S. In fact, primaries do it. And all long representations carry states that are annihilated by Q. You take a primary and act with Q on it. Okay? But there is no long representation that carries states that are annihilated by both Q and S. Okay? So this index, when evaluated on long representations, vanishes. This tells us that the index, this trace index, is insensitive to two short representations pairing up and becoming a long representation. Because if you had two short representations that had the charge of a long representation, so that they could pair up and leave, then those two short representations by themselves don't contribute to the index. Because no long representation contributes to the index. And therefore, this index is invariant under complete constant renormalization. Is this clear? It's a simple argument, but sometimes a bit subtle. So tell me if it's clear. Any confusion about the argument? Okay. Just the fact that the index evaluated on any long representation. It's actually very easy to, if you don't believe my argument, you can just check. You remember, we computed the superconformal character formulae. So you can take that superconformal character formula and minus 1 to the power f is the same as e to the power I pi j, right? Because we want something that carries half integral charge, maybe e to the power 2 pi ij to be minus 1 and everything with integer charge to be 1. So we can take that character formula, plug in this relationship for the chemical potentials, put minus 1 to the power left as an imaginary chemical potential for j, and you'll just see that it's 0. Remember, character formulae for long representations are trivial to write down because they're unrestricted. It's precisely because they're unrestricted. You see, for each, let me just remind you how it worked. Suppose I wanted to write down the character for a long representation for this algebra. Okay? Let me do it in the language that I've written down above. Okay, let me do it in the language that I've written down above. This would be, and I'm writing it down and you tell me if you believe me. This would be e to the power minus beta delta, where delta is the weight of the primary. Sorry, I shouldn't call it delta now. E naught, where E naught is the lowest energy or scaling dimension of the primary. Okay? Then we would get e to the power, we would get the SU2 character for spin j. SU2 is simple enough that we could write down an explicit formula if you wanted. Right? It's like something like e to the power, what is it? sorry, zeta 1, something like j plus half to e to the power minus zeta 1 j minus half by e to the power zeta 1 by 2 minus e to the power zeta 1 by minus zeta 1 by 2, something like this. I may have got some factors wrong, but some very explicit thing. The SU2 character for the primary, SU2 character for the primary under left moving SU2, similar SU2 under right moving, similarly an SUM character, a U1 charge. If the U1 charge was Q, this would just be e to the power phi Q. Let me put a minus sign there, sorry. Minus, all of them are minus, relative signs. E to the power phi q. This is all dealing with the primaries. Nothing interesting happens there. But then we have one factor for everything that causes descendants, right? So for instance, we would get the factor of e to the power, oh God, where is it? Zeta 1 by 2 plus zeta 2 by 2 times e to the power beta minus beta. 1 minus this for one of the derivatives. For a second derivative, we would have 1 over 1 minus e to the power minus zeta 1 by 2 plus zeta 2 by 2 e to the power minus beta. And two more such factors, right? 1 by 1 minus e to the power minus zeta 1 plus zeta 1 by 2 minus zeta 2 by 2 e to the power minus beta times 1 over 1 minus e to the power minus zeta 1 by 2 minus zeta 2 by 2 e to the power minus beta. These are the factors for the derivatives. Is this clear, everyone? Because derivatives have plus j1, j2 plus minus half. And then we would have similar factors for each of the q's. Okay? So we would have similar factors for each of the q's. We would have one, now not in the denominator, in the numerator, 1 plus the charges associated with each of the q's, except it would be 1 minus because of the minus 1 to the power left. Okay? And we would have the charges associated with each of the q's. Okay? But remember, because of the condition we put, we would have one such factor for each of the q's. One of the q's is our special q. Because of the condition we put, this thing here is 0 for that q. And so we get 1 minus 1, so we get 0. Okay? So this trace, evaluated on a long representation, is manifestly 0. Just because of the factor of 1 minus charges for that particular q. You see also, Kanu, that had we not put this condition, this trace would not have been 0 for a long representation. Had we not put this condition or one similar for one of the supercharges, this would not have been 0. So this trace is in general not protected because it doesn't vanish for long representations unless we put that condition on chemical potentials. Is this clear? Well, beyond for making this sum of charges equal 0, the motivation is we want to invent a protected quantity. So one way of saying it is we want to invent a trace that will vanish in all long representations. Another way of saying it is we want to invent something that, it's the same thing, that cannot be renormalized. You see, a trace over, right, let me remind you of the basic arguments. The basic argument is that in any short representation, all charges are integrally quantized and so cannot change continuously. Okay? Charges in a short representation are integrally quantized and cannot change continuously. Okay? The only way the charges of short representations can change is if they combine together, become long representations. Then they can change. So if we can invent a trace that runs only over short representations, in such a manner that which is the same thing, long representations, this trace evaluated on long representations is 0. Then this trace cannot be renormalized. Because even if two short representations combine together and make a long representation, they combine together in units such that they would have contributed 0 to this trace.
Because the final product is 0.
Because the final thing is 0.
Can we actually check from the definition of this index
Yes.
that if we take derivative with respect to any of the chemical potentials,
Yes.
that derivative vanishes? Because that is in a sense beta, zeta, these are also some parameters.
Yes?
If you change these parameters, this index should not change.
No, it will change. See, first you have to only take those derivatives that commute with this condition.
Yes, so you have to take derivative with respect to this derivative.
Del and that. And then when you take those derivatives, it will change. It's not true that this quantity is not a function of these chemical potentials. It is a function of the chemical potentials. What it's not a function of is a coupling constant. If we take a line of theories and we vary along that line, there the index cannot change. Okay? Now, there is going to be a chemical potential with respect to which it does not change. And that's coming in a moment.
Yes, that's a combination.
There's that combination.
Yes.
Okay? But the most general chemical potential it's a function of. And that's coming in a minute. Okay. Other questions, comments?
So in the beginning, you said that delta is equal to 0 or it's non-zero. In that case, you get some Fermi.
Right. So all states with delta not equal to 0 don't contribute to the index. Yes.
That non-zero is always a positive value or negative value?
Always a positive value because it's the right hand side of a commutator of Q with Q dagger. So that delta is positive on every state follows from the fact that it's the right hand side of Q with Q dagger. Okay? It's either 0 or positive, cannot be negative.
So this statement that non-representation does not have states which are annihilated by both Q and S, is that easy to see from such an expression?
That do not have states that are annihilated by both Q and S? Yes. Well, at least we've half seen this because we've seen that this trace evaluated on the long representation is 0. Now, you might trace only gets contributions from states that are annihilated by both Q and S. Now, you might worry that perhaps there are many different states, each of which is not annihilated by Q and S, but they conspire together to give 0. But, yeah, okay, let's see. Okay, good. We can see it in the following way. See, this factor here, okay, a long representation is one where we can take the primary and act with it on Q and not get and get a non-zero state. Okay? So, all states in a long representation are Q on primary and other things acting on it, other things not involving Q, or primary and other things acting on it, other things not involving Q. By other things I mean P's and other Q's, the raising operators. Right? All states are of that form and we can form these long representations unrestrictedly. Okay. These states, okay, are annihilated by S. Why? Because the primary is annihilated by S. Sort of by definition. And this guy will go through all the other things. Now, why does this guy go through all the other things? Right. It's basically this. You see, the Q, the only thing it might not go through is a Q. Okay? Now the Q with okay, it might not go through P also, but that will produce a Q. Should be possible to answer your question very explicitly. Let me ignore this for a moment. Suppose I can ignore taking the S through this stuff for a moment. I'll come back to that. Okay. In this case, this S annihilates the state if you allow me to take this through for a moment. Okay? And so then we're done with these states. With these states, in the same way, Q annihilates these states because Q squares to 0. Okay, now I have to argue about the taking through. I think I would have to think about that argument. I mean, it's certainly true, but I would have to think about making the argument.
What is this bit? Long representation?
Anurag wants to see not abstractly, but just by an enumeration of states. Just by enumerating all the states in this. Oh, but you know, there's an easier way. Sorry, I'll tell you in a minute. He wants to see that you just by enumerating all states, okay, you cannot form any states annihilated by both Q and S. Actually, Anurag, the easier way. Sorry.
We can argue that if let's say that is true, that you have a state such that it's annihilated by both Q and S, then any general state is a combination of primaries and descendant states.
Yes.
Now, if Q annihilates it, we need Q to annihilate it. We also need Q dagger to annihilate it.
Yes.
So if Q annihilates it, it has some charges.
Yes.
And if Q dagger annihilates it, if Q dagger acting on it has the negative state of all of those charges.
Yes.
So for both of these to be equal, the charges will have to be 0. Right? You need to have a null state to begin with.
You could have states with delta equals 0 that are annihilated by both Q and Q dagger.
Right, but you needed to have Q acting on You needed to have Q acting on it to give you 0.
And Q dagger acting on it to 0, and that's consistent provided delta is equal to 0.
But each of these states would be raised by Q, right? So if you had a lowering operator, that would be possible. But if you have some primary plus descendants, you're always creating a state which is something plus some.
Something plus charge. But okay, good question. Siddharth is asking, what is the delta charge of Q? Okay, delta charge of Q is 0. This we can check explicitly.
This is what the condition says. In the condition you used Q charges.
No. But I'm telling you now about the delta charge, the thing that comes on the right-hand side of the commutation relation. That, evaluated on Q, is 0. So, I don't think the argument works. Because if you started with delta equals 0, it could have remained delta equals 0. And maybe I haven't understood your argument. I mean, what is wrong with the possibility that you have a delta equals 0 state, which is annihilated by both Q and S? Such states exist in short representations. You are, I think, suggesting that, see, because it's annihilated by Q, then it's not a long representation. Yes. I think that's basically right. And this is the argument here. We just have to make sure that taking things through doesn't change things. Right? Because the primary was not annihilated by Q. How do you know that after acting with some descendants, it's still also not annihilated by Q? That's the only additional element, if I've understood your argument right. But Anurag, there's actually a very easy way to answer this. And you remember that all representations obeyed a BPS bound. So delta was greater than equal to something. Okay? Using that BPS bound, it's very easy to make this argument. Because it's the same as the question of are there any states in the theory which obey delta equals 0? Okay? Now, you can just evaluate the charges of all the descendant operators, all the Q's and P's. Okay? Now, from the BPS bound, we have an inequality that tells us that the dimension is greater than or equal to something in terms of other charges. We know what the charges of all the Q's are. Okay? So, using that, you can, in 3 lines, show that if the primary obeys this BPS bound, and since I know the charges of all the descendant operators, there's no state in the algebra that obeys delta equals 0 unless that equality is saturated.
So it has to be shown.
Yeah, it has to be shown. This is one way of doing it. I think one could argue logically as well, but this is one way of doing it, and this is one thing I have done at some point. Okay, so it's easy to show, just very explicitly. Yes?
So you said it does not depend on coupling constant. Right?
Yes.
So what does it mean it doesn't depend on coupling constant? Is the beta function?
It doesn't depend on coupling constant?
Yeah.
Okay, so if you have a line of fixed points, a line of theories depending on some parameter, which I'm going to call a coupling constant. Example of this is n equals 4 Yang-Mills theory as a function of its coupling constant lambda. So suppose you have a line of fixed points and you move along this line of fixed points. This index cannot change. The trace over the Hilbert space of this theory, this particular trace, and the same trace over the Hilbert space at some other value of the coupling has to be the same.
This is superconformal, right?
Yes.
So it should not anyway depend on energy, which is like mass or something, the length.
No, but you see, these are either the energy on a sphere or scaling dimensions. Okay? So, what we're doing is taking the superconformal theory and computing the partition function of the superconformal theory on an S3. Despite, say, free scalar theory is conformal, your argument just needed conformal, right? Okay, so a free scalar theory is conformal, but it has some spectrum on the S3. The reason it can is because the S3 has a length scale in it, namely the radius. Okay, so it has energies. All energies have to be some number by R. That's what scale invariance tells you. But there's a set of energies. And the set of energies is the same as the spectrum of operators of the theory, scaling dimensions. Okay, so it has a non-trivial, this partition function is non-trivial. It's not like the partition function itself is trivial. The partition function is non-trivial, but it cannot vary continuously with a coupling constant unless the theory undergoes a first order phase transition and the spectrum of the theory jumps discontinuously. More than a first order, I don't know, zeroth order phase transition, spectrum of the theory jumps discontinuously. It's a violent phase transition. I just made that word up. Okay. Right. All good? Yeah, well, what is true is that when you take this trace and expand it as e to the power minus chemical potential times number, the numbers behind that have to be either positive or negative integers, correct, because of the minus 1 to the f.
So you're saying two short representations can have equal and opposite contributions and they cancel when you
Exactly. All good? Okay, now let's try to take Sunil's statement and make that a little more precise. Let us remind ourselves what supergroup we were dealing with. Okay, so we were dealing with the supergroup SU m/4. Do you remember? This was one of the supergroups we talked about. You remember that this was a sort of nice supergroup in which this block was m cross m, this block was 4 cross 4, and then we had the q's and the s's here. Okay? And you remember that this supergroup worked because all charges were in vector representations of both SUM and SU4, but SU4 happens to be the same as SO6. And a vector of SU4 happens to be the same as a spinor of SO6. Right? So this SU4 part was like the space-time part. And that's the SO4 comma 2. Okay? Some appropriate real version of this. It's like SO6. And this part here was the SUM times U1. You remember the structure of this group, right? Okay. Now, you can ask the following question. You can ask, what is the largest supergroup what is the largest subgroup of SUM comma 4? Subgroup as a sub-supergroup, sub-super Lie algebra. Okay? That commutes with Q and of course also S. Okay? Now you see this Q or its negative guy S. Okay? Q, let's look at Q for a moment. Q was the Q's, the set of all Q's transformed in the bifundamental under SUM times SU4. It was fundamental under SU4, fundamental under SUM. Okay? So we could ask, what part of SU4 commutes with Q? I'm not dealing with the U1 separately. Let me talk with the SUs. We'll put the U1 in at the end. Okay. What part of SU4 commutes with the Q? So what's the answer to that, somebody? I've got an object that's a vector, that's a fundamental under SU4. So one element of that fundamental. What part of SU4 stabilizes that one element? It's similar. You know, you've got a vector, you've got 4 cross 4 matrices acting on it, and you've got the first element. We want to keep this guy fixed. So, if everything's inside this 3 cross 3 block, it'll do the job. So it's SU3, perhaps some additional U1 part. Forget that for a moment. As far as the SU2 part is, it's SU3. Similarly, what part of SUM commutes with this one guy? Well, it'll be SUM minus 1. Okay? So it will not surprise you very much. It will not surprise you very much to know that the maximal commuting superalgebra is, well, I'm writing it down and I'll check it for a moment in a minute, will be SUM minus 1 slash 3. Right? At least it has the right. Let me just check I've got this. Yeah. If I keep real forms, this was SU2 comma 2. Anyway, I'm not keeping the real form. The right version of this is that the maximum, the way I've written it in the papers, I've got to put this factor here. This is SU2 comma 1 slash m minus 1. That's keeping careful track of the real version of this. Okay. I think SO4 comma 2 was SU2 comma 2. So The original thing was 2 comma 2 slash m, and it goes down to 2 comma 1 slash m minus 1. Okay, so it's will not surprise you very much to know that this is the maximal commuting super Lie algebra. Any questions about this? This can be checked. Not hard to check. Okay. Now, why is this relevant? You see, when we compute this trace, even when we compute it for short representations, we only receive contributions. Oh, so I should have said this before. Okay, let me rewind for a minute. First, we only receive contributions from states with delta equals 0. So, in response to Diksha's question. Okay. Notice that in general, our let's count the number of parameters that our superconformal index depends on. Okay, so it depends on beta, it depends on mu1, it depends on what I call it zeta 1, it depends on zeta 2. Okay, and what do I call these guys? Okay, whatever I call them, the mu I, the m minus 1 chemical potentials for SUM, and I think we called it phi, which was the chemical potential for the U1. So if I total this up, how much do I get? I get 3 plus m, so m plus 3 chemical potentials. Okay. Then on the trace we put one condition. So we get m plus 2. Okay. By the way, this in the case m equals 4, this is 1 less because we don't have the U1. So in the case m equals 4, the total number of chemical potentials becomes 6. This is very easy to see. It's the 3 cartons of SO6 and the 3 cartons of SO4, 2. So that's 6. Okay. So we get one condition. This becomes m plus 2, and for the case m equals 4, this becomes 5. M equals 4 is special because n equals 4 super Yang-Mills soup. It's worth keeping track of separately. Okay. So you might at first have thought that we have an index that is a function of m plus 2 different parameters. Or in the case of n equals 4 super Yang-Mills, an index that is a function of m of 5 parameters. However, Diksha has pointed out that that actually there's a fake. Why is there a fake? Why there's something here that's not correct. Why not? You see, all states that contribute to the index have delta equal to 0. Right? All states that contribute to the index have delta equal to 0. Therefore, the chemical potential that couples to delta, actually the index doesn't depend on that. Right? So if I find a chemical potential that couples only to delta and no other quantity, so I choose a basis of my Cartan charges where delta is one of the terms in the basis. I put a chemical potential coupling to that. The index is actually not a function of that chemical potential because delta is equal to 0 for all states. That's different from this because you see the charges that appear in delta are very different. They involve Rk, for instance, for all k, where this one only involves R1. Right? It's a completely different condition. Okay? Therefore, the actual information in this theory is not an m plus 2 numbers. It's actually a function not of m plus 2 parameters, but actually of m plus 1 parameters because delta is equal to 0. Is this clear? In the supersymmetric index is being computed over a set of charges where one of the charges is just set to 0. So if we wait with the chemical potential with respect to that charge, we may think we're getting a new function, but we're not. Because all chemical potentials are, those charges are just 0. This clear? Okay. One can word that as an equivalence between, I mean, in any basis, one can word that as an equivalence between index with some values of the chemical potentials and index with some shift. And the shift is governed by those charges. Okay. Here, in the case of m equals 4, it actually depends on 4 parameters. Okay. This also tells you why the index is not a complete accounting of supersymmetric states. You see, all supersymmetric states always obey a BPS bound. In this case, the BPS bound was simply delta equals 0. Okay? States were supersymmetric and we were focusing on those states that had delta equals 0. Okay? Now, therefore, all supersymmetric states can only depend on one less than the maximum total number of chemical potentials, because one charge is 0. But in addition to that we see, that's this thing that we just talked about. But in addition to that, we had this other constraint on chemical potentials. So, another way of saying that is that out of the total number of charges in our problem, supersymmetric states are those with the lowest energy for fixed other charges. So we always get one less parameter in supersymmetric states than in regular states, because the energy is the minimum, not arbitrary. However, the index is a function not of one less chemical potential than general, but two less. Is this clear? Right? M minus 3 has gone, m plus 3 has gone to m plus 6 has gone to 4. Right? Two less. And this tells us that it's not the most general partition function over the set of supersymmetric states. If we had a 5-parameter partition function for n equals 4, not the most general partition function over the set of supersymmetric. So we're not recovering all information about supersymmetric states from this way of thinking. One parameter less. This is happening because of minus 1.
Computing the differences, not the number of states.
Yeah, or perhaps a little more precisely, because as we saw, the number of multiplets of a given sort is not an invariant. But there's this one chain that is. And that one chain, of course, came because of minus 1 to the power. Okay? So this is a reflection of that. Okay, excellent. Fine. Now, the last thing I wanted to tell you about was the relationship. Okay, the last thing I wanted to tell you about was the relationship. Okay, between this trace thing and these chains with numbers of representations that we discussed before. Okay, so for understanding that relationship, where we go back to this. Okay, so the commuting supergroup was SU 2, 1 slash 3 slash M, sorry, M minus 1. It would be slash 3 if we were doing n equals 4. Okay. Now look, we know that the index in the end receives contributions only from states that are annihilated by both Q1 and S, by both Q and S and delta. Okay? So, the set of states that it receives contributions from, okay? The set of states that it receives contributions from transforms in a character of the part of the superalgebra that commutes with Q, S and delta. Okay? Because all these other charges can act on these states and transform them around. So what I'm saying is that it logically follows that this index here should be expandable in terms of characters of this commuting superalgebra. Okay, so the set of all states inside a representation that are annihilated by Q, S and delta transform in a character of this commuting superalgebra. Because it commutes, it doesn't spoil the fact that it was annihilated by Q, S and delta. Right, you've got a state, it's annihilated by Q and S, you act with some supercharge, it doesn't spoil it from being annihilated by Q and S because it commutes with Q and S. Okay? So this index here can be expanded in characters of this commuting superalgebra. And what we did in this paper is the following. We asked, suppose the full representation content of the theory was some number of short representations of all possible sorts of the original SUM slash SU2, 2 slash M theory. Okay? Now, each representation of SU2, 2 slash M, we can evaluate the index on that representation. And what I've just told you is that that index, when evaluated on any particular representation, gives you some character of SU2, 1 slash 3 slash M minus 1. Is this clear? Okay. Now, question, what are the coefficients? So we know independently, we know all the unitary representations of SU2, 1 slash M minus 1. So we know all the possible characters that can appear on the right hand side. Question, when you take the representation of SU2, 2 slash M, evaluate the index on it, it becomes some character of SU2, 1 slash M minus 1. First question, is it the case that two different representations of SU2, 2 slash M evaluate to the same character on SU2, 1 slash M minus 1? Does that ever happen? Answer, yes. It happens for those representations that form part of the same chain. Okay? Therefore, if you evaluate the index on the most general state content of the original theory, and then you get sum over SU2, 1 slash M minus 1 characters with some coefficient. What is the coefficient of each of these SU2, 1 slash M characters? Answer, it's the chain. N minus N plus N minus N plus N. Okay? Now, index is protected. SU2, 1 characters are linearly independent. They are a basis for all functions of these chemical potentials. Okay? They are linearly independent. You can't form two of them as linear combinations of the third. So the protection of the index is the same statement as the protection of the coefficient of every SU2, 1 slash M minus 1 character. But we checked explicitly in this paper that these were exactly the chains I told you about last time. And therefore, the non-renormalization of this index is exactly the same as the group theory statement that those chains are not renormalized. Moreover, we demonstrated that every chain that is not renormalized appears as the coefficient of some SU2, 1 slash M minus 1 character. And therefore, there is exactly as much information in the non-renormalization of this trace formula and non-renormalization of every possible chain. Okay?
So the main simplification is you get rid of this supergroup if you check for the invariance of the quantity which stays constant.
Yes.
It's just the change, not the full.
Yeah, the chains are the real data, numbers of some number of representations. So if you're thinking group theoretically, that's how you think. However, this trace here is a much more physical object because it's a trace over a Hilbert space. And traces over Hilbert space we are good at computing. So these chains are nice to think about it in abstract group theory terms, but they're hard to actually compute. Whereas this trace here is something we can compute using path integrals. What is important is that there is no more information in the conservation of the chains than there is in this trace. So the fact that this trace is not conserved tells you all the information about non-renormalization that comes from group theory alone. Could be you have a special line of fixed points where some dynamics gives you additional non-renormalization information. That is fine. But the non-renormalization that comes from group theory alone is entirely exhausted by the conservation of this minus 1 to the power f thing. Okay? This ends my general discussion of the superconformal index, in which I've tried to explain to you the structure of the non-renormalization and how it's all contained beautifully in a trace formula. Any questions or comments about it? In the rest of the lecture, I will satisfy Schumann and we will try to evaluate these. We'll try to evaluate this index for n equals 4 Yackel state. Please go on. Oh.
So we could have defined some other case which was annihilated by some other case. This you choose a particular case which was lowest weight in SU.
I chose a particular one. Actually, yeah. I should have said, we need to do this plus the corresponding one for one of the Q bars. Okay, but since by doing this, we got all the chain information. That is a demonstration that whatever else you did, you could not have got more information.
Yeah, so I was going to ask basically the evaluation. If you chose some other Q, are those traces maybe not fully robust under the evaluation?
Well, yeah. I think all Qs are basically symmetry identical. Maybe if you show some linear combination of Qs.
Yeah, basically, I'm saying you can define a trace which can count half BPS or quarter BPS trace. Some of them, half BPS trace is more robust as compared to quarter BPS.
Right. You could ask, is there some trace formula that counts quarter BPS states? Right. Really, in some sense, these states here count 1/16th BPS states because there's all states that are annihilated by 1 Q out of 16. You could ask, is there a trace formula that counts, let's say, 1/8 BPS states, for instance?
You will have more conditions on beta than
Exactly. So certainly there is some limit of this index that counts half BPS states. But about 1/8 BPS states, I think not. Because you see, at least, it depends on which 1/8. Let me say a little more. Diksha is asking, you remember we had this Q1, where this is referring to a particular SU. Let me talk about super Yang-Mills theory, n equals 4 super Yang-Mills theory. Okay, we have this Q1, which is, there I'll use SO6. So this is Q half, under the Cartans of the SO6, and this was minus half under J1, and was 0 under J2. Okay, now you could ask, what about states that are annihilated by both this Q and Q plus half, 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 half. So therefore, it's annihilated by states which are of the form Q alpha, half, half, half. Okay, this is a question people ask a lot. The set of such states is called the chiral ring. Okay, and it's studying states that are annihilated by these, or states that are annihilated by these quantities, modulo states that are exact under these quantities. Is something that you can do even for non-superconformal theories, for supersymmetric theories. The condition modulo states that are that are exact under this in superconformal theories is not necessary. This is exactly the equivalence between cohomology and harmonic functions. Do you remember states that are annihilated by D modulo states that are D times something is in one-to-one correspondence with states that are annihilated by D star plus D star D. Right? The second thing was harmonic functions, the first was a cohomology. Exactly the same arguments. Here tell you that states that are annihilated by Q, modulo states that are Q exact, are in one-to-one states, correspondence with states that are annihilated by Qs plus Sq, and therefore by both Q and S. Okay? So this chiral, if by 1/8 BPS, we mean this particular 1/8 BPS, annihilated by both these Qs, then it's sort of easy to analyze what these conditions impose. Basically, you need to satisfy a BPS bound for Q half as well as Q minus half. The thing that changes in the BPS bound is that we have this 2j that will become a minus 2j. So we'll get the same condition on the right hand side, except you be added to it the condition j is equal to 0. Okay? So in the case of n equals 4 Yang-Mills theory, these are states that are created by the 3 chiral superfields, phi 1, phi 2, phi 3, and 2 of the fermions that have a spin under J2 but not J1. Okay? Now, these are indeed particularly special states. Okay? Now you can ask, if you have these 1/8 BPS states, what kind of multiplets do they appear in? And one can show that they appear in multiplets that lie at the edges of these chains. Okay? So you remember there was something special about the chain at j equals 0, which then went and ended with a specially short representation. Okay? One of these specially short representations is one of these 1/8 BPS guys. Okay? Now the point is here that you see these 1/8 BPS guys don't live by themselves. They conserved. These special 1/8 BPS guys can decay at the expense of creating a 1/16 BPS guy, because they're in the same chain as 1/16 BPS guy. However, there are even shorter representations. Okay, there are even shorter representations which sort of form chains of length 1, like the half BPS representations are of those sort, or just never appear on the right hand side of the BPS algebra. So let me say this again. You see, do you remember the discussion last time about how something could be renormalized? Okay, the way something could be renormalized is this. If there is a long representation, okay, if there is a long representation such that limit epsilon goes to 0, chi of long is equal to chi short plus chi short. Okay, then this chi short can combine with that chi short to be renormalized. But it may be that there are some very special representations whose are so special that their characters never appear on the right hand side of such a relationship for any long representation. If that is the case, then those representations will just by themselves never be renormalized. Okay? And the half BPS states are like that. Okay? And in fact, all of these appear as a coefficient of some character in this 1/16th BPS index. Some SU2, 1 / m-1 character in this SU2 in this 1/8 BPS index. So there's no more information about any protection than what you can get from this index. Okay? Now, it's true that you can do special things to try some for these half BPS guys. For instance, you can take a particular limit, which I've forgotten now, but you can take a particular scaling limit of the chemical potentials that appear in this index, and that will become an index that contributes only to half BPS. But everything can be done starting with this. There's nothing new that you get from anything else. Have I answered your question?
Yes, yes.
Okay. Yes.
So you made a comment that SU4 vector is a scalar under SO4.
Yes.
What is that?
You take the 4-component representation of SU4, the defining representation of SU4, fundamental representation of SU4, and you ask, we know SU4 is the same as SO6. What representation does it become under SO? I mean, what name do we give it when we think of it as a representation of SO6 rather than SU4? Well, the dimensionality of the representation is something invariant. So it has to be a 4-dimensional representation. What 4-dimensional representations do you know of for SO6? Chiral spinor. So it becomes a chiral spinor. And the anti-fundamental becomes the anti-chiral spinor.
Okay, one more question.
Yes?
So in the conformal group, you said it's SO42.
Yes.
But in a book I read it's SO51. What's the difference?
In what?
In a book I had read the conformal group is SO51.
Well, the book you read was probably talking about the conformal group of R4. We are talking about the conformal group of R3, 1.
That's a Euclidean and
Euclidean and Minkowskian, I presume. We're always working in Minkowski space.
but what's the difference between SO42 and SO51?
What is the difference between them? Do you want to know mathematically or physically?
The Lorentz image is still the same, right? In both.
No, I don't think so. I think that what was an SO3, 1 subgroup of SO4, 2, the analog of that is SO4 for what you're doing. So, you see, if you start with 1 time, the conformal group develops 2 times because it's SO4, 2. If you start with no times, the conformal group develops 1 time. So that extra time that's generated, I mean, time is quote unquote, right? The extra minus direction is coming from the conformal, the p's and the k's. So your SO5, 1 is probably the conformal group of R4. Right? Yeah. And of course, mathematically it will come presumably by just doing t goes to it. Okay? All good?
You expanded the index in linear combination of SU2.
Yes, let me write it out. First step, we start with step 1. Most general index is equal to sum over ni and then trace minus 1 to the power f times e to the power minus beta, all of these chemical potentials with those things. okay, evaluated on representation Ri, where Ri forms a complete set of short representations of the original theorem. Okay, Ri are representations of SU2, 2/m. But because this index here only receives contributions from states that are annihilated by delta, it can in fact be written in terms of characters of SU2, 1/m-1. Okay, so this becomes Ni chi. Let's call this R of R, Ri of Ri, R of Ri. You know, what character you get when you evaluate this trace on which bigger representation. Okay? Where these chi's are characters of SU, characters of SU2, 1/m-1. Okay? So always we get this structure. This evaluates to this. In general, it could have been. It could have been. Turns out not to be. 1 goes to 1. We just checked it in our paper. It wouldn't have made a difference if it had been, but it turns out not to be. Okay? If it had been a linear combination, it would better be linear combination with integer multiples. It could have been, but yeah. Okay. Now, important question here is what kind of map is this? Is it 1-to-1? Is it many to one? Clearly it's not one to many. That makes no sense. You evaluate on something, you get something. But you might be able to evaluate on two different things and get the same something. So is it many to one or 1-to-1? Answer, it's many to one. Two different upstairs representations, when you evaluate the index on them, can sometimes give rise to the same character.
Why this Ni is not changing?
Because Ni is a number. This is this. Okay, Ni is number of representations of type I, short representations of type I. Now, turns out that it's many to one. Now you can ask which representations upstairs give you the same character downstairs. Okay? And it turns out to be along those chains. Okay, in fact, you get this up to a sign. There's a plus minus sign here. Okay, and the plus minus sign is determined by which position you are on that chain. Okay, so now you get sum over Ni minus 1 to the power I along a chain times chi. Okay, now this chi has many different chemical potentials. Right? So, evaluated on different representations, you get linearly independent functions. So, each of these chains is therefore protected. That protection follows from the protection of the trace. And the great thing the nice thing we showed is that every chain appears as a coefficient of some chi. So, there is no protected information that is not in this quantity. Is this clear? Excellent. Okay, so fine. So now for the last part of this, lecture, let me, yeah. Didn't understand. Say again. Yes. Yes.
Those correspond to different representations, the states in the representation which are annihilated by different Q's and different S's.
Different Q's and different S's. Very good. You see, I am not sure I've understood your question, but your question might be this. I have picked a very particular supercharge. How could it possibly be that that very particular supercharge gets information about everything? Because this is only information about the states that are annihilated by that very particular supercharge. What about the information about the states that are annihilated by some other supercharge? Is this your question? That's good. The thing is that states appear in representations of SU2, 2 / M. And that representation is sort of covariant. Right? It doesn't single out any particular supercharge. So, the same representation will have some set of states that are annihilated by one Q, some set of states that are annihilated by another Q, and that's true for every Q. Okay? And therefore, by looking at states annihilated by one particular Q, you lose no information. Okay? It's a little like this. Suppose we were in a theory, we were looking at states in representation theory. If we were looking at states that were eigenvalues of Jz, it doesn't matter which Jz you choose, it carries all information. Right? Because of rotational invariance. It's not like you get new information by changing your basis to Jx. Right? Yeah. Okay, excellent. Fine. So now the final question we're going to address in today's lecture is how do we compute this index in any realistic case? Okay? The realistic case I'm going to study is n equals 4 super-Engels there. Now, this part of the lecture is a bit achronal because I was going to start dealing with 4-dimensional gauge theories, tell you about them more systematically and so on, but okay. So for this part of the lecture, we'll understand many of these things as we go along. But for this part of the lecture, I'll throw 2 or 3 things at you. First, there is this theory with m equals 4. 4 times the minimum, so 16 Q's and 16 S's. Okay? That is superconformally invariant for every value of a coupling constant, which I'm going to call lambda. This is just true. Or G squared Yang-Mills if you want to. Okay? This theory exists. And this theory has the following state content. Okay? It is the states of this theory are 6 scalars. All the fields of this theory are in the adjoint representation. There's so much supersymmetry that all the fields of the theory are in one supermultiplet. Okay? There's so much supersymmetry that all the fields of the theory are in a single supermultiplet in the sense of strategy. They're all in a single supermultiplet in the sense of strategy. And because they're all in a single supermultiplet, they all transform the same representation under the gauge group, namely all the adjoint, same as the gauge field and therefore the adjoint. So there are 6 scalars. It has a gauge field, all in adjoint. Okay, so this is 6 degrees of freedom, and then there's a gauge field which we'll count as 2 degrees of freedom. It's within 4 dimensions, so the transverse polarizations are 2 in number. And then there are fermions. There are 4 chiral fermions. This is 8 degrees of freedom. Can somebody help me to count the number of degrees of freedom in 4 chiral fermions? Two degrees? 4D. How do you count fermionic degrees of freedom? In the units in which one real scalar field has 1 degree of freedom. Do you know what degree of freedom counting is? What does it mean? How many components? Even more precisely, how many functions do you need to specify on a given time slice to determine future evolution? Okay? So for a real scalar field, that's 2. You need to specify phi and phi dot. So if you need to specify 2 functions, we count that as 1 degree of freedom. 2 real functions, we count that as 1. So with that counting, how many degrees of freedom are there in a chiral spinner? D equals 4. Good. Half of 4. Excellent. Excellent. Half of 4, because it's chiral spinner, so it's 2 component, but it's complex. So there are 4 real scalars, each of which is first order. So the evolution is specified by 4 pieces of data. 4 pieces of data we count as 2 degrees of freedom. Right? So there are 4 chiral fermions, which has 8 degrees of freedom, which matches the bosonic degree of freedom of the theory. Always degrees of freedom match between bosons and fermions in a supersymmetric theory. Okay? Now, I have to tell you a little more about this theorem. Okay. So, the R symmetry of this theory was SO6, same as SU4. Under SO6, the scalars transform in the vector representation. In a vector representation. Under SO6, the chiral fermions, as we've just discussed, transform as chiral spinors. Whether chiral or antichiral, we'll get back to it. And the gauge bosons are neutron. Okay? Excellent. So, now what I want to do is to compute the trace, this superconformal trace in this theory. Okay. So the first thing I have to do is to write out the formula for delta. Okay. So now in this particular theory, I'm going to use the language H1, H2, and H3 as the Cartan charges of SO6. And I'll never talk about SUM and U1. There's no U1 first. Won't talk about SU4, just because SO6 is more familiar. H1, H2, and H3 are very familiar. Just rotations in 3, 2 planes, right? Okay. So, in this theory, my Q, where carried charge is half, 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 and carried charge is minus half. Okay. And in this language, let me write down what, okay, I'll, great. Beautiful. Let me write down the charges of various fields in this theory. Excellent. So, let's first start with x, y, and z. You know, the 6 scalar fields, I break up into 3 complex pairs, x and x bar, y and y bar, z and z bar. Okay? These in an n equals 1 sense are chiral fields, where q is one of the charges of that n equals 1 algebra. And the antichiral fields are their complex conjugates. I know we're doing this all achronally. I mean, if you don't understand everything I say in this part, you will understand in 4 or 5 more lectures. Okay, fine. So this guy carries charge 1 because it's the scalars have dimension 1 in 4 dimensions. They're protected, so it doesn't get renormalized. 0, 0 because they have no angular momentum. Okay, and these guys carry charge 1, 0, 0, 0, 1, 0, and 0, 0, 1 under the SO6, right? Because you see, x and x bar make up one of the 3 two-planes. So the x is the guy that has charge 1 under rotation in that two-plane, x bar, and so on. Okay. Then, of course, you have the complex conjugates of these guys. We have x bar, y bar, z bar. Okay, these carries charge 1, 0, 0, and these guys carry charge -1, 0, 0, 0, -1, 0, and 0, 0, -1. Okay. Then okay. Then we've got the fields okay. So you see, we've got the chiral superfields, chiral fermions, and their complex conjugates. The complex conjugates are antichiral. We're in 4 dimensions. Okay? So totally we've got 8 of these we've got 8 of these fermionic fields, half of them chiral, the other half antichiral. Okay? So let's first look at the chiral fermions. Okay. So the chiral fermions are those that that carry charge psi alpha. Okay. 0 under the second SU2. Okay. And now we've got charges of a chiral spinor. So let me write out these charges. These charges are half, because it's a fermion, carries dimension half, plus minus half, because it's chiral fermion, plus half and minus half, and 0 here. Okay? And these guys are charges of a chiral spinor. Oh, wait. Sorry, these were of an antichiral spinor, anti-F. Antichiral spinor. And so these charges here could be either plus, plus, minus, total number of minuses has to be odd. So, so plus, plus, minus, or plus, minus, plus, or plus, minus, plus, plus, or minus, minus, minus. Okay? Similarly, there are the complex conjugates of these guys. Okay. There are the complex conjugates of these guys. These carry 0, alpha, and here now, under complex conjugation, minuses become pluses. Okay? So total number of pluses has to be odd. So it becomes a chiral spinor. Okay? Okay? So you get a chiral spinor, and this chiral spinor here, okay, this chiral spinor here, it's got what is charges? Well, it's dimension half. This is 0, this is plus minus half, and here we get plus plus plus, plus minus minus, minus plus minus, or minus minus plus. Okay, and finally there's the gauge field itself. That's A mu. Okay, and A mu is not actually physical in the sense of it's not actually a physical operator. Okay, because physical operator, we'll talk in terms of operators or states by the state operator map. Okay, it's easiest to think in terms of operators. Okay, so instead of that we'll write F mu nu. Okay, so F mu nu, which is gauge invariant, it's a good operator. And what is this? Well, F mu nu is antisymmetric. So antisymmetric transforms under the 1 plus 1 of SU2. So this is dimension 2, 1, 0 plus dimension 2, 0, 1. Right, because antisymmetric was adjoint, and adjoint was adjoint of SU2 plus adjoint of SU2. Okay, and here it's uncharged. Okay, so of all the fields in the theory, we've written down the charges of all these fields. Is this clear? Yes? Those are the charges under SO6. Those are these charges, yeah. They transform in some representation of SO6. That representation is anti-chiral spinor, and therefore can have these charges. Is this clear? Okay. Now the next thing we need to know is what is delta. The next thing we need to know is what is the formula for delta in these variables where we don't have these horrible RIs, but we have nice civilized HIs. Okay. Now, delta is equal, the thing that appears on the right hand side of the Q commutator S is equal to E minus sum over I, let me just write it out explicitly, minus H1 plus H2 plus H3. And I think plus 2J1. Let me check that. Minus 2J1. Minus 2J1. Minus 2J1. That formula that I wrote down in general, if you translate to these deltas in the case m equals 4, you'll find this. Very nice civilized formula. Okay? Now, let us check various things. To start with, let us check what delta of Q is. So what are the charges of Q? So let's add another column here, another row here, which is Q. its charges are half, minus half, 0, and half, half, half. Okay? Now, what is, and let's add another column here. Which of these states have delta equals 0? Tell me, are these guys delta equals 0? Yes. What about these guys? No, the delta equals 2. Okay. What about these guys? Any of them delta equals 0? So let's see. We have delta is equal to half, because all of them are fermions, so they all have half. Now, we have either a guy with two pluses and a minus. Okay? So those guys would become 2 pluses and a minus, so that will become minus half. Right? Or we would get 3 minuses, in which we would get plus 3 halves. Right? Okay? And then there is minus j1, minus 2j1. So we get then plus minus 1. Now, question is there any way of adding up those charges to give you 0? If we choose a plus 3 half here, we're dead. That's not going to work. What about choosing the minus half here? That gives you half, that gives you 0, but plus minus 1. Doesn't work.
So those pluses can be added as
Half and minus half. These ones you mean up here? This one? R charges. Yeah. So that's minus this one. Plus, plus, minus, plus, minus, plus, and minus, plus, plus. And then there was minus, minus, minus.
those are halves actually.
Halves, halves, all minus. So I'm sorry. It's a spinner. I've not been writing the halves, but yes, it's always halves. I'm sorry about that. Yeah. Do you agree? Have I done this algebra right? Okay. So these guys, too bad. None of them have delta equals 0. What about these guys? Okay. What's the difference with these guys? Here we have delta is equal to half. Now there are two things that are different. This is different and this is different. Okay. So here we just get 0 because right. Right, here we just got 0 because it was J2 plus 0, and here we get, now again there are two sorts. There are the guys with 2 minuses, so that gives us plus half, or there are the guys with all pluses, which gives us minus 3 halves. Okay, I've done something wrong. One of the two sorts of fermions should have worked. Sorry, let me see. Yeah?
Why is there only one J1? Why J2 is not coming?
Because Q had only J1. Yeah. Just a minute. What am I doing? What am I doing? I'm so sorry. Half is in 2 dimensions, 3 by 2. We're looking at fermions in 4 dimensions. The dimension is 3 halves. Sorry about that. So now let's go through these again. This guy won't work. This guy will work. What? Yeah, I should change the list. Sorry. What? Q should be 3 half. No, no, Q is half. Q is square root of momentum. It's not, yeah, an actual spinner, yeah. Okay, now this works. You see, this guy with the minus half and this guy with the minus 1 will work. Okay, so the minus half was 3 of them, right? Right? Okay, so, and this minus 1 was when we had plus half. Okay, so here we get some supersymmetric letters, and let's see what they are. They are psi, half, 0, and then plus, plus, minus, psi, half, 0, plus, minus, plus, and psi, half, 0, minus, plus, plus. Okay. Now let me try this. This guy looks like it works. Okay. So this guy looks like it works. So this is, yeah, it's, I think what, in our notation we called it a lambda. So I'll just call it a lambda here, which is lambda, which is 0, and could be alpha, yes. 0, alpha, and then this is plus, plus, plus. Right. In n equals 1 language, this one I think is the Gaugino, whereas these are the Cairolinos. And okay, now what about the field strength? By the way, what about Q? Do you see? Because it's half minus 3 halves plus 1. So Q itself has delta equals 0. This is something I asserted at some point. Q is one of those guys with delta equals 0. Louder, louder. H, what is H? F. Let's see. Some of them will have delta equals 0. Okay. So F, we can have, so F, there are many Fs, right? So let's look at these Fs as plus, F plus alpha, F minus alpha, or F0 alpha. Sorry, what am I saying? F is either, F is in the antisymmetric of, yeah, so F is in the antisymmetric of SO4, and therefore is a vector under SU2 plus a vector under SU2. Okay? So let's call this F self-dual plus F anti-self-dual, where the self-dual guy is the vector under SU2 and the anti-self-dual guy is the vector under SU2 left, and the anti-self-dual guy is the vector under SU2 right. Okay? Now clearly the guy F anti-self-dual does not have delta equals 0 because it doesn't carry any H's and it carries its momentum under J2, whereas its scaling dimension is 2. So that doesn't work. What about the self-dual guy? It is 0 for one component, right? Because this guy is a vector under SU2 left, so its charges are 1, 0 or minus 1. right? So the guy that has charge, angular momentum 1, this will cancel this. Okay? Keeping track only of SU2 left charges, I'll call this F plus plus. Because charge 1 is like 2 charge halves. Okay? With the same notation, let me call this plus. Plus, plus comma 0, plus comma 0, plus comma 0. Okay, excellent. So now, what do we want to do? We're running out of time, but okay, I'll try to be quick. What do we want to do? Okay, we want to compute the partition, the index of n equals 4 super Yang-Mills theory. Now, we know by the state operator map that the index is the index over all states, but can also be thought of as the index over all operators. Okay? Operators in free, now we know that the index is not renormalized, so we can calculate it on the free theory. Operators in the free theory have dimensions, or all charges that just are additive in the dimensions of the fields that you put. Okay? So, we've got these fields here, and what we want to do is to basically do both statistics and impose gauge invariance. I'll come to that. Both statistics and impose gauge invariance on the set of letters with delta equals 0. Is this clear? Now, these letters are not all the letters we have, because we also, in addition to these, have derivatives. Okay? So let's make one more. Sorry, I should have left more place here. But let's make one more column here for derivatives. Which, so derivatives, there are 4 derivatives. Del plus plus, del plus minus, del minus plus, del minus minus. Which of these, if any, have delta equals 0? You know, a vector in SO4 is a spinor times spinor of SU2 times SU2. So plus plus indicates charges on the two SU2s, plus half under the 2 SU2s. Whereas plus minus will be plus half under the first SU2 and minus half under the second SU2. Okay? Clear, Kanu? Okay, so now tell me, which if any of these has delta equals 0? Has charges 1, half alpha. Okay? Therefore, E minus 2j is 0. On the other hand, del minus alpha has delta equals 2. So I'm not writing it down. So we can act with these derivatives and stay in the space of delta equals 0 fields. Okay. Last thing we need to worry about is equations of motion. All scalar fields obey in the free theory the equation del squared chi x is equal to del squared x bar, and similarly is equal to 0. Notice though that okay, there's one more thing that I wanted to Right. Notice though that all the gauge fields here, all the fields here, I didn't check this very carefully for you, but you could check for yourself if we go through again. All of these have delta equal to 0 or greater than 0. That had better be, right? Because a delta is q times s. Yeah, go on.
Why shouldn't we get, when you act with del minus alpha, you do get minus
Del,
with a del minus alpha.
yes.
So
Why do you get delta equals minus 2? You get delta equals plus 2.
oh, it's delta. Oh, right. Then.
Yes. Yes. Okay, excellent. Yeah. Okay. So these fields either had delta equals 0 or delta positive. If you act with an equation of motion on fields with delta equals 0 or with delta positive, you get delta becomes even more positive because del square carries delta equals 2. So equations of motion which will be important for us, the only things that will ever be important for us is the equations of motion in delta space, in the space of delta equals 0 things. So scalar equation of motion is not important. Okay. Now, what are the fermion equations of motion like? Fermion.
States coming from these operators doesn't.
What?
Not in the delta is equal to 0 state.
Say again?
States coming from these operators.
The subtractions you'll need to do are not in the delta equals 0 space, so we won't have to worry about them. Okay. Fermion equations of motion take the following schematic form. Del alpha dot. Okay. I should distinguish between raised and lowered because we're doing this SU2. They contract with epsilon. So del alpha dot psi alpha is equal to 0. This is an equation of motion for a chiral spinner. And del alpha dot psi alpha dot is equal to 0. This is the equation of motion for an anti-chiral spinner. Notice that the equation of motion for a chiral spinner is in fact anti-chiral and vice versa. That's because the equation of motion have gamma, and gamma changes chirality. Okay. Now I'm going to ask which equation of motion, if any, which equation of motion, if any, involving our four delta equals 0 spinners is itself delta equals 0. Excellent. So let's see. So let's look at the equation of motion. Let's look at the equation of motion of that guy. The thing that acts on psi plus has del minus. So you have del minus psi plus whatever equals 0. Del minus alpha. What? Okay. Now this guy carries positive delta. So this is not so no equation of motion for those guys is important. But what about the other guy, the lambda 0 alpha? Lambda 0 alpha. What about del plus alpha lambda 0 alpha? This guy, this derivative, is one of those derivatives. And therefore, delta equals 0. So this equation of motion is a delta equals 0 equation of motion. Okay. So let's write this equation of motion here. Okay, and finally, the last question is about equations of motion for this guy. Now, written in terms of F, Maxwell's equations have two parts. A, there's the Bianchi identity, and B, there's del squared F is equal to 0. Okay, del squared, as we've seen, always carries delta greater than 0. So it's not an equation of motion we have to worry about. But Bianchi identity we may have to worry about. Okay, so let's check what Bianchi identity, if any, carries F plus plus. Okay, yeah. We checked, I think none of the Bianchi identities are delta equals 0. Let me leave that as an exercise for you guys to check. Okay, so this list is now complete. Okay, these are the set of delta equals 0 letters. I think we're going to have to stop. We'll do half an hour in the next class to finish this. What was I? Let me tell you the route forward. What we want to do is now count this index, compute this index over all products of such fields, subject to the constraint that only gauge invariant operators contribute. Okay? So, subject to the constraint that, let me set one thing up and then we stop. So, what are we doing? What we're doing is trying to compute trace minus 1 to, so let's say it. What we're trying to do is to compute trace minus 1 to the power f, and now let's use notation that is better suited to this problem. So let's say x to the power delta, let's say mu1 to the, let's call it zeta 1 to the power j1, zeta 2 to the power j2, and let's say mu1 to the power h1, mu2 to the power h2, mu3 to the power h3. Maybe I'll write it as e to the power minus beta delta plus zeta 1 j1 plus zeta 2 j2 plus mu I hi. Suppose this is what we want to compute. Okay? Let's remember the charges of Q. Okay? So the charges of Q were as given as here, and so we get minus beta plus zeta 1 plus sum over I mu I plus mu 1 plus mu 2. This is our condition. Okay, we'll wait with chemical potentials subject to this condition. Okay, and finally, okay, so what we want to do is to compute this quantity. I'll do all the technical stuff later, next class. What we want to do is compute this quantity over the space of fields, over the Hilbert space of the theory. But the Hilbert space of the theory is one-to-one correspondence with the spectrum of operators in the theory. Operators in the theory are just products of these operators or supersymmetric derivatives thereof. And then the whole thing made gauge invariant. Okay? So this is the counting problem we have to solve. We have to compute the trace over this set of operators with the constraint of gauge invariance. Is this clear? Yeah, I won't try to. It's a simple problem to solve. It's not a hard problem to solve, but I will explain the solution next time. Sorry, was this class 2 fractured? I mean, was going to n equals 4 supersymmetric Yang-Mills, has it made sense?
I mean, we understood that there are some field content and there are some constraint on the fields, and in any calculation of index, if you know the field content, and you can calculate the index.
I'm done. Just one second. Yeah. Right. Exactly. So we will come back to n equals 4 Yang-Mills, and you'll understand why this is the field content and so on. But given that, it made sense, right? Okay. Fine. Thank you.